Hello everybody, welcome back to our radiation transport or radiation transfer equation. So in the last video we're talking about the radiation transport equation, sometimes also known as the radiation transfer equation. Yeah, you know, they have the same kind of acronym, but yeah, they pretty much mean the same thing. They are just equations to tell you how the radiation is affected when it travels through participating media. So the first thing first, we were talking about these four effects that happen to radiation as it goes through, let's say, a body. Alright, so let's do color to black. So yeah, that will have it at a black background. So it's much nicer. I must prefer black now. So that's how Khan Academy does it. Maybe I'll do it like that from now on. So anyway, the weakening effect. So first thing first, how do we think about the weakening effect due to absorption and scattering? So let's consider some radiation is going through in the medium. Okay, so what quantity would we use to describe radiation? So what quantity is best? What quantity is best used to describe the radiation? So we know radiation is affected by the frequency or the energy, the wavelength of the photon. It is also described, you have to consider the direction of it, and you need to, the direction, the solid angle, all of this comes into play. Right, so direction, solid angle, and frequency are important to radiation. Alright, so what then is the best quantity? So the quantity that takes all of this into consideration is intensity. Alright, so intensity is usually what we use to describe radiation. So some I lambda, if we use the intensity of the according to the wavelength, or sometimes in this textbook they use I eta. Can you see I eta? All right. Okay, so this is what is used inside the textbook. What it means is that, hey, eta is the wave number, so that's the other way, and you can use a frequency which is new as well. Alright, so we use intensity in general to describe radiation transport. Why? Because all of these factors are taken into account, especially the direction, especially the direction and solid angle. So all the direction, solid angle, and frequency, etc., is taken into account when we talk about intensity. So great. How is direction being taken into account? This is taken into account when we say, alright, we take energy per unit normal area. Notice I bolded the normal because that is what actually gives you the direction. Okay, so let's say we have radiation at some intensity that's going along the path, and then it goes through an area, and the normal area dA, and it goes through a very small path. Okay, so this length is, so this dA will be this cross-sectional area, this length is ds. Okay, so in this very short distance, the radiation exiting the system will be slightly weaker. Alright, so this is like attenuated. And then we can of course do very simple differential equation. So this is I at S, this is I at S plus ds, right? So let's do a quick balance. We can do a quick energy balance. So yeah, assuming assuming this I goes in, we can do a quick energy balance. So okay, we can say, let's go, energy accumulated equals to, okay, input, which is this. So we have I at this location S. So S is sometimes we don't like to use X, Y, and Z coordinates here because that we are not necessarily having radiation traveling in the X, Y, or Z direction. So we just use the direction S, or the length unit S, to describe, okay, this is the path that this radiation is going through. So it's IS minus I, okay, S plus ds. Does it make sense? This is the one exiting, this is the one entering. So what is the energy accumulated? It is this, and then you have to multiply into the normal area, dA. Right? So what is the energy accumulated then? Well, you can put like a volume. So what's the volume? It is ds dA times, alright, so this is the volume, and this is the rate of energy accumulation. Okay, so rate of energy accumulation per unit volume. Yep. Or energy accumulation per unit volume, or otherwise you can say energy absorbed per unit volume. This is for absorption. Okay, so if we do this, we can cancel the A's at both sides. Alright, and then we can divide both sides by ds. Alright, and what we get is just a minus dids at the end of the day. So the energy absorbed per unit volume will be equals to minus some dids equals minus rate of energy absorbed per unit volume. And how do we describe this then? Okay, so okay, what is the rate of energy absorbed? We can assume the rate of energy absorbed is proportional to I. I sub S, or I evaluated at S. So the rate of energy loss will be proportional to this what do you call that? This incoming radiation, right? So of course, if you have more radiation coming in, the more radiation you have to lose. So that should kind of make sense. So if you have a very intense beam, you pass through a medium, you lose a certain fraction of the beam. Then you have overall more absolute loss. So we assume that the rate of energy absorbed is proportional to IS. So I evaluated S times some proportionality constant. So what is the proportionality constant used? It is this little thing called K. This is the kappa n, or otherwise known as the kappa lambda, otherwise known as the absorption coefficient. So we use I here, it can be dependent on the wavelength, which is why I use lambda. Okay. Of course, the neater way is to just use this kappa lambda, I lambda. So yeah, this is the change due to absorption. If we are only purely absorbing this material. Okay, so all right. Now you can see in the textbook they use a kappa eta, which is slightly different because they use a wave number as the reference. So you have intensity per unit wave number. In this case, we use intensity per unit wavelength, so it's slightly different. But physically, they mean very similar things. So don't really have to worry too much. Okay, so this is attenuation due to absorption, and then we can think of outscattering in a similar manner. Okay, so outscattering, we can do the same thing. It's proportional to okay, outscattering, and this is the absorption term. So instead of kappa lambda, we use sigma lambda. Yeah, so again, when the radiation travels through a block, it can get scattered out into other directions, but we don't really care where it's being scattered yet. All we care about for the time being is that I have this radiation coming in this direction, and this radiation intensity leaving here in this direction. So that's all we are thinking about in this case. All right, we don't care about the other directions or the other solid angles that is going at. We just care about the main direction. Okay, so there's radiation coming in and there's radiation going out. So what's the difference between this and this due to scattering? So we can sort of think, okay, again, the more radiation you have coming in, the more radiation you get being scattered out. So using the similar logic, we can come up with the same equation, all right, which is this di lambda ds due to outscattering is equals to minus I lambda sigma lambda. Now sometimes it is convenient to combine both. All right, so sometimes it's convenient to combine both di lambda ds, and we call it extinction. This is the combination of both scattering and absorption. So I have this together plus this, and that's equals to sigma lambda plus kappa lambda into I lambda. All right, sigma lambda, I lambda. So these two, when they combine together, sometimes they call it beta lambda, otherwise known as the extinction coefficient. So the kappa lambda is the absorption coefficient, sigma lambda is that scattering coefficient. So we take a look at the textbook, it'll be pretty much the same idea. See, sigma is here, and then this is the total attenuation, and then you have this extinction coefficient over here. All right, so that's extinction coefficient for you. All right, so what is the total? Yeah, what is the total attenuation? So we can reword this as attenuation equals to minus beta lambda I lambda. Okay, so how then we can do some integration, and then we find that okay, this thing is going to be an exponential integral. All right, so if you integrate this, and it's purely outscattering and no inscattering, and it's purely extinction, there's no emission or anything like that, then di lambda over di equals to minus beta lambda ds. So if we were to integrate both sides, so we have a logarithm of I lambda over I lambda. So I'm going to take it at two limits, alright? So we're going to have integral of 0 to s, or big S, or just s, beta lambda ds. Okay, so got to make sure that this s here is not the same as this s here. All right, so because that kind of doesn't make sense for an integral. So the thing is, I have to make sure that the variable with where we are integrating here is slightly different. So I'm going to use a dummy variable. So I simply change this s into an s star to make sure things kind of flow properly. I mean, mathematically they look correct. Okay, so where are the limits? It starts at 0. So this is evaluated at s star equals to 0. Okay, and this is s star equals to s. So what is the picture we are seeing here? All right. So don't worry about the math. It may be confusing, but okay. So let's say we have some intensity starting off at s star equals 0. So s star is the dummy variable, and then it goes through some the medium, and then so this s star equals to 0, and this is s star equals to s, and then the final radiation coming out is I lambda s star equals to s at this point here. Okay, so during the traveling of the radiation, when the radiation travels through this medium, it will get attenuated. And this is the final radiation coming out. So okay, let's just do a exponential on both sides. All right, so I'm gonna copy and paste this here. We're gonna take exponential on both sides and get rid of the logarithm. So exponential of whatever's in this bracket. Okay, and I'm gonna shift this initial bit over. Alright, so you can see it's kind of an exponentially decaying thing. And of course, if this beta lambda was constant, then we can just say beta lambda s is the exponent, is what results from this integral. So beta, if your extinction coefficient was constant, so we will get beta lambda s. So you can see basically it's an exponential decay kind of a thing where when this radiation goes through. Okay, so yeah, all right, so one thing to note is that you see this quantity actually pop up so often, right? So this quantity is going to pop up often. It's going to pop up very often. Okay, so this is the special quantity which I think I want to start discussing about in the next video. So thanks for watching. I'll see you guys next time.